Professor Neeraj is an associate professor in the Department of Mechanical Engineering at IIT Bombay. His research focuses on combustion, molecular modeling, energetic materials, and Professor Neeraj earned his PhD in Mechanical Engineering from Pennsylvania State University in 2014, following a Masters of Engineering from ISC Bangalore. He aims to enhance the efficiency and environmental compatibility of high-energy materials and also works in molecular modeling using ab initio methods. He has contributed to several research projects funded by prestigious organizations such as DST, ISRO, DRDO. He will be speaking on use of machine learning to formulate novel propellant oxidizers. Let's welcome him on the stage.
So, good afternoon. So this is, since morning we have been having people from industry and from the services talking about a lot of things, all large scale industries, explosives, all kinds of field guns, artillery guns. So this is going to be less glamorous. And I also have the bad fortune of being scheduled in a non-prime time slot where we have had our ice creams and gulab jamuns. So you'll have to bear with me, but still what I think is deep reinforcement learning or machine learning is something that single word is capable of exciting people these days at least. So following up on what Dr. Manjeet Singh was telling, that these propellants, solid propellants, they are made up of fuels and oxidizers integrated into, casted into one solid block. So the oxidizer there is in a large way mostly what is used is ammonium perchlorate. The question is fundamentally, can we start thinking about molecules that can substitute ammonium perchlorate, or can we come up with new oxidizer molecules? So this is something, a thought in that direction. We are not, the TRL level and all, we are not even, I don't think we are even talking about that yet. But if you are to look for it, how to look for it? It's going to be a molecule. So oxidizer has to be a molecule which contains oxygen. It's going to be a molecule, how should it look like? Now the possibilities are infinite. There are 120 plus elements in the periodic table. You have to put them together along with oxygen and form a molecule. The possibilities are infinite. So how do we narrow it down? So that is where, although a human being can think about it, but the number of possibilities are so immense that a machine may be able to do a better job in thinking about it rather than. So we are in the process of developing a deep reinforcement learning model for the design of novel propellant oxidizer molecules. So the aim here is to fabricate a deep reinforcement learning based computational strategy for design of novel molecules, and then of course design an oxidizer metric based on a neural network architecture. Because what is a good oxidizer? Of course something that contains oxygen, but then that's not all. There are some other properties that it needs to have. So we don't need to go too much into this. We know, all of us know what is artificial intelligence, what is machine learning, what is deep learning. So one of the simplest model of machine learning is linear regression. You have an input, it goes through an activation function, and you have an output, y equals mx plus b. So x is your input, y is your output, and your job is to find m and b, so that given an x, you predict the correct y. When this, instead of just having one activation function and one input, if you have multiple inputs and multiple activation function, we call it a neural network. And here you have a single hidden layer of activation functions. If you have more than one layer of activation functions, we call it a neural network. So it's basically these nodes are the human neurons, and then the connecting parts are the nerves. So there are neurons in our brain which are connected by nerves, and there are the electrical signals, thoughts in the form of electrical signals flow back and forth. So this is, you're basically trying to mimic the human neural network. And what we have particularly used here is called reinforcement learning. So reinforcement learning is something, it comes at the intersection of so many different fields, primarily computer science, engineering, and mathematics. What is reinforcement is, when you're training a machine, you want it to behave in a certain way biased towards some particular behavior. Here we want our model to generate molecules that have a high oxygen balance and that have some other desirable properties. So we want our model to behave in a biased manner. How do we bias it is, imagine that you're training a dog. If the dog behaves the way you want it to behave, you'll reward it. and because of the reward, the dog will know how to behave, it will continue behaving that way. So that's how we train this model. We use something called as reinforcement learning. So again, first of all, now we want to generate a new molecule. How do we generate a new molecule? We generate a new molecule by, we have to have a computational way of representing the molecule. So there is a standard way of doing that, that is called as SMILES, Simplified Molecular Input Line Entry System. So it's basically a series of strings coded in a certain way, and any series of strings will give you a unique molecule. What model do we add? So again, we don't have a lot of time to dwell deep into the mathematics or the technical aspects of it, but basically we have a generative model that uses a gated recurrent unit with a stack. So this is called as a stack augmented RNN. What it does is, it has the capability of generating SMILE strings by adding a character one at a time. It first calculates the probability, then it, so this is the overall model, and the generative model is this one. What it does is, it takes the first character of the string, calculates the probability of the second character based on the first character, and then based on that probability generates the second character. Then it compares that character to the training data, and based on the loss function, based on the error, it modulates the parameters of the model. And then we have several layers of these, so that from the starting to the ending, you keep on adding the strings. So this is how the model is trained, and this is how the trained model is used to generate new data. So you, based on probabilities, you go on adding strings and you get a new model. So the database that now we need a database to train our model. There are a large number of molecular databases available. The problem is, we don't have a database available for energetic molecules, and more particularly energetic oxidizers. We don't have a database for that. So we just took what is called as the ChemBL database, which has a huge number of molecules. It has something like 1.5 million or so molecules, and some molecules are very crazy. We don't need them, because if we want to generate oxidizer molecules, our database has to have molecules which are similar to our molecules, and these definitely are not like that. So we just have to pull out the molecules from that database which we are not interested in, and so we have to refine that database. So database has been cleaned to remove all the molecules having elements with an atomic number higher than 20, and we have also removed some very complex molecules. We have also removed molecules like chlorine, fluorine, sulfur, beryllium. We don't want them in the oxidizer, because again, although it's a propellant, it is meant to be loaded in missiles and destroy things. We still want it to be environment friendly. So we eliminate those molecules. Why do we eliminate lighter molecules? Is because it's a propellant. So when it generates thrust, and if heavy molecules are coming out of it, the higher the molecular weight of the exhaust product, lower is the ISP or the thrust. So we want light molecules. So again, because this ChemReal database has millions of molecules, we just want to test our model first. We test it on a reduced set of 1500 molecules, and then just analyze how it is doing, so that once we know it's doing well, we can train it on the full set of molecules. So this is just a result slide where you can see those units in GRU layer are, so these are the technical specifications of model, how many GRU units you use, how many stack units you use. But then there is something called as valid molecules. So valid molecules means this model, why is it's not yet generating any oxidizer molecules. It's just generating novel molecules that are valid. Valid in the sense valency is satisfied, rings are closed properly, there are no unpaired electrons. So again, so if you train it less, only 34% of the internal, only 84% of the molecules are valid, and we can't do much better there no matter how much we train it. So epochs means for how much units of time have you trained that model. And then again, whichever molecules are valid, not all of them are internally unique. It also gives you duplicate molecules. And then novel molecules, and molecules that are duplicates, also some of them are from the training data itself. It's not generating new molecules. So internally unique molecules are further less. So this was just a test of the model, and these are some of the molecules it generated. And then this was the first stage of training. That is, it was generating molecules that are valid, that are stable, can exist, at least in theory. Then we have to reward it. So there are some reward functions we had defined. One is a exponential reward, linear reward, binary reward. Basically, If the oxygen balance is greater than 0, oxygen balance means you have oxygen atoms in the molecule, and if you burn it, some oxygen will go into burning that molecule itself. And we have to have some balance oxygen to burn the fuel then. So oxygen balance has to be 0 for a good propellant oxidizer. So if the oxygen balance is 0, we reward it. If the oxygen balance is less, we don't reward it. We say the reward is 0. And then if we do this, then you see, with the exponential reward function, we can see that as we train more and more, the best performance we can get is 74% of the molecules are valid, new, good oxidizers. So this is just a graphical representation of those results. So we see before training, the red curve, most of the molecules are in the negative oxygen balance range. After training and after generating, the number of oxidizer molecules increases. And then this was done, different reward functions, and then as I said, we reduced the size of the model and trained it. Now we trained it on the full data set. After training it on the full data set, we are actually able to get about 98% of unique new novel molecules. And but the issue again was just oxygen balance is not enough. The molecule has a lot of oxygen, but does that make it a good oxidizer? Obviously not. So what we have to do is we have to list down the properties of a good oxidizer, which are oxygen balance, of course, synthetic accessibility. Yeah, you have a molecule, but can it be made in reality? So there is something called a synthesis accessibility score. It should be below 6 if it is to be synthesized. Then specific impulse, it's a rocket propellant property, which is the thrust per unit mass flow rate. So higher the specific impulse, better the molecule. It's like mileage for a car, higher the mileage, better the fuel. And then you have, so density has to be higher, heat of formation has to be positive. There are so many properties an oxidizer need to have. So we cannot just train the model on oxygen balance, we need to train it on other things also. So that is something we are in the process of doing right now. What we will have to do is, this input is oxygen balance and synthesis accessibility score. Right now, that model we have trained is on 2 things only, high oxygen balance, a good synthesis accessibility score. But in the future, what we will have to do is, we will have to come up with a metric, give weightage to each of the property, and then calculate a total weighted score of the oxidizer, and then say, that score has to be maximized. So we have to train the model based on that score. But what that score should be, what the parameter, what should the weights of those different properties, we don't know that. What would be the best number? So even for that, you can train a model, machine learning model, to get the best weights to calculate the oxygen performance score, kind of oxidizer performance score. We can do that. So right now we have trained the model like this, oxygen balance and synthesis accessibility score. We have 3 hidden layers, 96 nodes in each layer. And so it has generated about 26 novel oxidizer molecules. We have some comments here which says, okay, this molecule, it is an inorganic compound, but it's highly unstable. So then we may not be able to go with that. There are some molecules for which no records have been found. Have people attempted to make them, or what is the status, we don't know. But if such molecules, then we'll have to work on further. So these are the 26 molecules, and this is just and this is a graph here that shows those molecules on a scale which says synthesis accessibility score. See, if it is higher than 6, it's difficult to synthesize. If it's lower than 6, it is better. Some of those molecules are actually natural products, so natural products typically have that kind of a synthesis accessibility score, and those kinds of the percentage of population. So we can see that all those dots, the molecule that the model came up with, has a low synthesis accessibility score, which is encouraging. But at the same time, we have to explore the other properties also. So yeah, I'll keep with time. I don't want to overshoot the time. So we actually, to some extent, have succeeded in developing a model that can generate good oxidizer molecules. We need a lot of work on this model. And at this point of time, again, I'll reiterate what Professor Atre was, or even General Pandey was in the morning saying, that we actually don't have an integrated system of, so suppose this research is to be taken further. So we have to further develop this model, develop those molecules at lab scale in a chemistry lab, maybe here itself, then go to some industry which can scale it up, then do small scale motor testing, static motors testing, then do the actual testing, and then induct them in the army. As academia, we can only go as far as developing this model and maybe developing the molecules at a milligram scale in our lab. But then we need an ecosystem which exists outside the institute to work with us and come up with novel molecules that can go into our solid rocket motors in the future. Okay, so with this, I will end, and thanks for your patient